Welcome to Mrs. Miller's notes for her pre-calculus class. These are the notes for section 1.5, day 2, entitled Equations. And today we're going to talk about completing the square, the quadratic formula, and absolute value equations. So these concepts should be review. Now remember that completing the square is actually a way that we can take a non-factorable quadratic and make it factorable. So like it says here, if the equation is not factorable already, then we can solve it using a technique of completing the square. So we're going to take a trinomial and make it into a perfect square trinomial. So what we essentially do is we move the c term over to the other side. If you have ax squared plus bx plus c equals 0, we're going to take this c term that we can't find the factors of to get to the b term. We're going to move that over to the other side. And then we'll take half of b and square it. And that's what we'll add to both sides of the equation. So that's the important concept to making a binomial into a perfect square trinomial. So let's review the process as we go through an example here. So we have part A and part B for example 6. And if you just look at part A, it's already set equal to 0. So you would think, okay, I have to factor this, but there aren't any factors of 13 that are going to add up to 8. So that's a problem. Now, we could use the quadratic formula for this. But if you really want to factor, the way we have to factor is we have to make this into something that is factorable. So what we're going to do is we're going to subtract the 13 out of there. That's that c term. So we're going to get him over to the other side. So we'll have x squared minus 8x equals a negative 13. Okay, now this negative 8, and I purposely left this space here because we're going to fill it in. This negative 8 now is the term that I want to divide by 2 and square it. So 8 divided by 2 is 4, and 4 squared is 16. So I'm going to add 16 to both sides. So I'm filling in that little blank spot there. So now I have x squared minus 8x plus 16 equals 3. Now I have a trinomial that I can factor. So the factors of 16 that'll get me to 8 are going to be 4 and 4. So this would be x and x and 4 and 4. And I want them to get me to a negative 8, so I need them both to be negative, and then I need them to multiply to a positive 16. So there we go. Now actually, we can rewrite this as x minus 4 squared equals 3. And now this is like an example that we saw in yesterday's notes where we have a squared term that we have to get rid of. And to do that, remember, you take the square root of both sides. So that radicand is going to pop out, the x minus 4. But remember, when we physically take the square root of both sides as part of our problem-solving strategy, we have to make our radical positive and negative. We need a plus minus square root 3. So then to finish solving for 4, I would add him over to the other side and get 4 plus or minus the square root of 3. Now since we have an answer in that form where we have a real number and a radical, it's actually better to do this completing the square process instead of the quadratic equation. I think this is a little less messy. You're dealing with more whole numbers all the way through, and even if we did the quadratic equation, we would still have this radical left over in our answer. But I think this is a little nicer, especially when you get down to these last couple of steps here. It's still very clean when you're dealing with the radical. You just get a square root of 3, and then you add the 4 over, and you're done. The quadratic formula is going to be a lot more messy when you're simplifying with that radical in there. But we'll deal with that in our next example. Let's finish up example 6 part B here. And this one's a little trickier because we have a lead coefficient. We have that 5 out front. But I still can't find factors of 5 and 10 that'll get me to a 20. So if you try and do a guess and check method, you're not going to find them. So again, we're going to start by subtracting that 10 over to the other side. So I'm going to have my 5x squared minus 20x, and I'm intentionally going to leave a little spot there, equals negative 10. Now before I take half of my middle term and square it, I have to take out that lead coefficient as my GCF. Now I know technically these terms also have an x as their GCF, but I don't want to take any x's out because I need an x squared and an x so that it stays as a quadratic. So you just take out that numerical GCF. So that's the tricky part for this one. That's the extra step that's different between part A and part B. So now I have x squared minus 4x. So this is my B term, that negative 4. So I take half of that, which is 2, and square it, so that's 4. So I'm going to add 4 to both sides. So I'll write that in as an extra step like I did before. Now when you're doing this yourself, you don't have to write it in as an extra step. You can just kind of fill in that little blank there. I'm just showing every single step as we go through. Oops. Now actually, before I move on, we don't want that to be just a plus 4 there because it's not really plus 4. I added a plus 4 inside the parentheses here, but that plus 4 is being multiplied by a 5. So I'm really adding 20 to both sides of my equation. So I have to have a negative 10 plus 20. So now I have a perfect square trinomial that I can factor. So I'll leave my 5 out front, and then I'll have my parentheses, x and x. Factors of 4 that are going to get me to 4 are going to be a 2 and a 2. And I need both of them to be negative. And then this will add up to a positive 10. Now I can rewrite this as 5x minus 2 squared equals 10. I can divide that 5 out of there. So x minus 2 squared equals 2. And then I can take the square roots of both sides to get rid of that squared. So my radicand pops out. And now I have a plus or minus square root 2. And then I have to add that 2 over to the other side. So 2 plus or minus square root of 2 will be my final answer. So again, watch out for any lead coefficient. You'll have to take it out as a numerical GCF. And then any number that you add in when you're completing the square, remember to multiply that by that numerical GCF. And that's what gets added on the other side of the equation. Okay, now let's review the quadratic formula. You should know the little songs for these. I can sing the songs in class, and I can sing them right now. But there's a couple little songs. There's the Notre Dame fight song, and then there's Pop Goes the Weasel to help you remember the quadratic formula. But it's opposite b plus or minus the square root of b squared minus 4ac all over 2a. And the a and the b and the c, remember, those are just your coefficients in front of your quadratic and your linear and then your constant. Okay, so here we have 3 examples. We're going to practice the quadratic formula. So for part A here, we have 4x squared plus 12x plus 9 equals 0. Remember, when you do this, it needs to all be equal to 0 first. So your A value is going to be 4, your B value is going to be 12, your C value is going to be 9. So if we substitute in, we'll have x equals opposite b plus or minus the square root of, let's see, b squared minus 4 times a times c all over 2 times a. So then when we simplify that, we want to start inside our radical. So I'll still have my negative 12 out front, but then I'll have plus or minus. Let's see, 12 squared is 144. And then 4 times 4 is 16, times 9 is also 144. So I have 144 minus 144 all over 8. So 144 minus 144, that's going to be 0. Square root of 0 is 0. So I actually get negative 12 plus or minus 0 all over 8. So really that's just negative 12 over 8, and that would reduce to negative 3 over 2. So I get one real solution. And we're going to talk about the characteristics of the value inside the radical sign and the type of solution you get after we finish these other two examples. And I'm actually going to switch colors here, so that way all our work won't blend together. For part B, I have 2x squared minus 3x minus 1 equals 0. So in part A, we had all positive numbers. Here I have a negative value for B and a negative value for C now. But we're still going to substitute in like we did before. Let me start my work over here a little bit. So we have x equals opposite b, so that would be negative negative 3, so that's positive 3, plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. So I'm going to simplify inside my radical again, kind of like order of operations. 3 squared is going to be 9. And then you can think of this as 4 times 2 times negative 1 and then subtract them. Or think of it as negative 4 times 2 times negative 1. Either way, we're going to get a positive 8 all over 4. So that's going to be 3 plus or minus the square root of 17 all over 4. And actually, that's all I can do for this one. That's as simplified as that answer is going to get. I can't break down 17. It's not a perfect square. I can't take out a perfect square. So we're done. So there I actually got an irrational solution. And I actually have two of them. This plus and minus tells me that I have one answer if I add the 3 in the radical, and then another answer if I subtract the 3 in the radical. Okay, now part C is going to be slightly different. Again, we have all positive values, but the type of answer we get is different from the other two that we've gotten so far. And let me change pen colors again here. So when I substitute, let's see, I'll have x equals opposite b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. So again, I'm going to simplify inside my radical, just like I'm doing order of operations. So that's going to get me 4 minus 8 all over 2. Now 4 minus 8, when I simplify that, that's where I have a unique case that we haven't seen before. I'm still going to have my negative 2, and I'm still going to have plus or minus, but inside my radical now I get a negative number. I can't have that. I can't have a negative inside my radical. So the way we get around that is we break it apart into the square root of 4 and the square root of negative 1. And we call the square root of negative 1 I. That's our imaginary number. So we actually get negative 2 plus or minus. Now the square root of 4 is 2, and the square root of negative 1 I'm going to call I, and then it's all over 2. And I can reduce that. So I would have negative 1 plus or minus I. So that type of an answer is actually a complex solution. It means there aren't any real solutions. This is an imaginary number. I have two imaginary solutions, so they are considered complex. Now, this next slide was extra room in case we needed it, but this slide is in your book. and it shows the connection between the value of the discriminant and the type of solutions you get. So if the discriminant is greater than 0, you get 2 real solutions. So I'm going to go back for a moment and I'm going to look at example B. In example B, my discriminant value, I'm going to change colors again, my discriminant value is right here. It's 17. This is 9 plus 8. Okay, that's my discriminant. And its value is greater than 0, so that means I get 2 real solutions. Granted, they're irrational, but they're still real. The irrational set is inside the bigger set of all real numbers. So if I knew that right away, if I knew that that was 17 and that was greater than 0, then I could know before I finish the problem that I'm going to get 2 real solutions. Now if your discriminant is equal to 0, like we had back in example A, right here, this 144 minus 4, that's a value of 0. When that happens, you get 1 real solution, and that's what we got. We got 1 solution. It's a real number. So knowing that ahead of time can tell me the type of solution I'm going to get. And then the last one here is if D is less than 0, then it has no real solutions. And when you're less than 0, you're a negative number. So that's what we had here. We had a value of -4 for our discriminant. And that got me no real solutions. I didn't get any real solutions. I got 2 complex solutions. So knowing those characteristics and the connection between the discriminant and your final answer can be important, because if you know that discriminant value ahead of time, then it can tell you how many solutions you're going to get and what kind of solutions they're going to be. Okay, we have one last example, and it deals with absolute value equations. Now remember, when you take the absolute value of something, you actually have 2 things, 2 values that you could take the absolute value of to get you whatever solution you would like. So for example, in this case, if I just had an absolute value of x equals 25, technically that x value could be 25. 25 is 25 units away from 0, or x could also be -25. -25 is also 25 units away from 0. So when you set up your absolute value equations to solve them, a lot of times students just want to solve the equation that they see, but really you get 2 cases. You have a case where the stuff inside the absolute values could equal your solution, or the stuff inside your absolute values could be the opposite of your solution, that -25. Now, depending on who you've had for teachers in the past, they might have told you to take, for this second case, they might have told you to make the 4x negative and the 11 positive and then set it equal to a 25. I think it's easier and that there's less risk of error if you just take the stuff that's inside the absolute values and set it equal to a positive solution and a negative solution. Okay, it'll have the same effect, you get the same answers, and you're only changing one number instead of 2 or 3 or 5. Okay, so then we have to solve each of these equations. So we're going to add the 11 over. So we get 4x is 36. When we divide by 4, x is going to be 9. So now that tells me that if I put 9 into that problem, I should get a value that gets me the positive 25. So 4 times 9 is going to be 45. Oh no, 36. Sorry, 4 times 9 is 36. Minus the 11 is 25. So that works as a solution. Then over here, I'm going to do the same steps. I'm going to add the 11. So this time I get 4x equals -14. And now when I divide, I get x equals 14 over 4, which is -7 over 2. And actually, if I substituted that back in, I would get, let's see, -7, can write it over to the side, 4 over 1 times -7 over 2. 2 goes into 4 2 times, so that's really like a -14. So -14 minus 11 gets me a -25, and the absolute value of that is 25. So that also works for my solution. So remember, when you're dealing with an absolute value equation, you want to set up two cases. You want to set up two equations to solve and check your answers. Okay, so is your set of homework problems for this evening. If you have any questions, come on in before school and see me.